Before the course begins, please complete the questionnaire on the screen to record your attendance. We will conduct 3 questionnaires throughout the course. Participants must complete all questionnaires to receive an attendance certificate and 2 hours of CPD credits. Welcome to today's Micro-credential Topical Course. This course is funded by the Environment and Conservation Fund and organized by the Hong Kong Green Building Council. First of all, we would like to express our sincere gratitude to the Environment and Conservation Fund for their generous support. Today's topic is Air Ventilation Assessment and Sustainable Building Design, Method and New Insights. We are honored to have Professor He Yun Yang, Research Assistant Professor at the School of Architecture, the Chinese University of Hong Kong, as our speaker today. Now, let us welcome Professor He to begin his insightful presentation.
Thanks for Hong Kong GBC's invitation, and I'm very glad to have this opportunity to join the ECF Fund program to have the 2-hour study journey with all of you guys sitting here and joining us online. Before I start today's lecture, I would like to give you a bit background information of myself. I'm Aaron from School of Architecture, CUHK, and my position is Research Assistant Professor. My study background is in urban wind environment and urban microclimate, particularly in the high-density cities. And my research aims to explore the answers to questions like how urban morphologies, our designs, our building design, architectural design, and climate change's impact on the urban environment, and how we can use the climate-responsive design strategies to improve our living environment. So, for today's lecture, my focus will be on air ventilation assessment and sustainable building designs. So I will have a brief overview of the methods of the air ventilation assessment and CFD, as well as sharing you some new insights from our recent research. So this is the contents for today. We will have 4 sections. Before I going into the methods of the AVA, I would like to have a brief introduction of some fundamental aerodynamic knowledges for architects and urban practitioners. And I will also have an overview of the building and urban ventilation design guidelines in Hong Kong. And after that, I will introduce you the 3 main methods that we usually use to assess the urban wind environment. And finally, I will go into the methods of the AVA. So let's start our section 1, Aerodynamics for Architects and Urban Practitioners. So the very first questions from you guys may be why wind is important in high-density urban areas. So we know we can experience wind every day, but we may not think about these questions. So every one of you may have different answers to these questions, but I believe that most of these answers will fall into the following aspects. So the first one is for achieving thermal comfort. Of course, because wind improves thermal comfort in hot periods by enhancing the convective and evaporative heat loss from the human body, making us feel cooler. So this figure showing us the 6 main factors that are affecting the thermal comfort of people, of us. And wind definitely is one of the major contributors in these 6 factors. And in the spatial dimensions, we will feel warmer and hotter in urban area compared with the rural area in the same city. This is because urban development has a greater impact on the local climate of a city. One of the best known effects of urbanization is urban heat island effects, which develops when urban cooling rates are slower than rural ones. So this is the figure I captured from the Hong Kong Observatory's website, showing that actually the temperature difference between the city center and the rural area in Hong Kong can be over 2 degrees Celsius during the nighttime, meaning that we will feel hotter, right, during the nighttime in Hong Kong, in the urban areas. And consistent with these findings from the Hong Kong observatories, we recently did observation study using over 100 automatic weather stations across Hong Kong and Shenzhen to have investigation on what is the magnitude of the urban heat island intensity in this region. And we find that actually during the study period, summer 222, we find that in the urban high-rise area in Hong Kong, these urban heat island intensities will go over 2 degrees Celsius, which is consistent and in line in the findings reported by the Hong Kong Observatory website, right? And we also find that in Shenzhen, this number is even larger and can go up to 3.3 degrees Celsius, meaning that they may suffering more discomfort conditions due to the extreme heat. So this means that for people living in urban areas, we may need more winds to cool down our urban surface and to make ourselves comfort. And in the temporal dimension, we will feel hotter today compared to 100 years ago. So this is again a record from the Hong Kong Observatory, showing that in the past 100 years, there is an increasing chance of the number of extreme hot weather events during daytime and nighttime in Hong Kong. So, this is because the climate change issues and the temperature is rising globally, so making our temperature is growing, so the number of extreme hot weather events is increasing accordingly. And we can expect that in the near future, the temperature will continue to increase, and we will need more wind to cool down our body and to cool down our urban area, to save the energy and to keep us health and comfort. And more than achieving thermal comfort, another important role of wind is to help us to mitigate the air pollutants and anthropogenic heat. In this micro-scale study, it shows that traffic pollutants and anthropogenic heat are easily trapped inside the deep street canyons, while wind can accelerate their dispersion. So you can see from these pictures that if there's wind that can enter into these deep street canyons, some of the pollutant and the anthropogenic heat can be released through this wind flow. Okay. So in a larger scale, in a calm condition without ambient wind, traffic pollutants and anthropogenic heat may accumulate over the urban areas. In comparison, if we are under windy condition, these emissions are direct downward and dispersed outside the city. And these two phenomena, we call them urban dome and urban plume. So this again demonstrating that if we have wind, we can have better air quality and we may have more comfort atmosphere in our city. Okay. And more than the benefit that we can obtain outside, for the indoor environment, we can also get benefit from wind. So another role of the wind is to improve the air quality. With good ventilation, the concentration of the aerosols and the airborne virus particles is reduced, and they are removed from your home more quickly compared to conditions with poor ventilation. So this is the diagram showing that the concentration of the aerosols and the airborne virus particle is reduced if we have a better indoor ventilation conditions, better natural ventilation. So, okay, we have already know that we can get a lot of benefits from wind. So the next question you may ask is maybe how urban morphologies influence wind behaviors. So without knowing the answers to this question, we may not be able to better decide, to know how to design our building so that they can adapt to the climate change, right? Adapt to the ambient wind conditions. So we are going to answer this question in the following part. So the urban climatologists are very smart. They are trying to find the answers to this question by using two simple and basic urban units. So because they know that if they are going to study the relationship between the urban morphologies and the wind environment using the complicated urban system and the urban morphologies, this answer may be more difficult to find because there are so many uncertainties with the complicated urban morphologies. But by using this isolated building and urban street canyons as the examples to show the relationship between the wind and morphology, the answer can be more clearly obtained. So, by studying this climate process within these two basic units, the isolated building and the urban street canon, scientists seek to identify the general wind behaviors and to integrate these findings to explain the airflow patterns at the city scales. So for these basic units, for example, for the isolated buildings, they figure out some basic air movement patterns. For example, at the wind wall side of cubic buildings, we can see this upstream vortex. And at the lead wall side of the building, we can see the building wake. So this is the very basic air movement surrounding the cubic buildings. And at the lateral side of an isolated building, we can also observe patterns of the flow separating from the prevailing wind. This is because the building are obstructing the original path of the prevailing wind, making the flow is separating at the corner of this lead wall side of the buildings. And you may notice that from this figure, the building orientation play an important part here. If the orientation of the building is different, the flow separation pattern is different accordingly. Okay. And more than this airflow movement, the scientists also identify different flow zooms according to the patterns of the flow surrounding the building. So from the left-hand side to the right-hand side, they define zoom A. They define zoom A, zoom B, zoom C, and zoom D. So zoom A is the upwind area, which is an unobstructed zoom, or we can call it a free stream velocity zoom. So here the wind is not affected by buildings. And when the wind approaching the building and go over the buildings, we will go to the zoom B. This one they call it displacement zoom or transition zoom. So the flow is transition here. And then at the immediate lead wall side of the building, they call it carotid zoom, meaning that the flow here is recirculate, and the flow usually has a weak wind speed but a strong turbulence intensity. So the wind here is quite weak. And then for the zoom D is the downward recovery zoom, and the flow will gradually recover after they passing the buildings. So this is the vertical section, and this is the plane section. So these two figures showing us that how complicated the flow patterns surrounding a building by passing through it from the upwind to the downwind. Okay. More than that, the scientists also figure out the characteristics of the shape of the vertical wind speed profile when passing through simple isolated buildings. So they defined type 1, 2, 3, 4. So you can see that they have different shapes of the vertical wind speed profile. So this is again the four zooms then surrounding this isolated building. Okay, and the air movement is also affected by the shape of the buildings. So if we putting the building in this way, the longer facade, the longer dimension of the building is perpendicular to the prevailing wind. They will generate a larger cavity regions, and here there's weak wind regions, and this region will be large because the frontal area of the building facing to the prevailing wind is large. But so in this situation, we will have a higher form jack. This is the form. They will generate higher form jack, but lower friction jack, and which is not good for air passing through these regions. But if we put our building in this way, we put our longer facade parallel to the prevailing wind, so the wind can more easily passing through the buildings, and they will have lower form jack and higher friction jack accordingly. So they will more easily passing through the buildings, and the cavity behind the building may be smaller, and the weak wind regions can be reduced. So after talking about some basic air movements around the isolated building, let's go to talk about another basic unit, the street canon. A street canon is actually consists of one street and two buildings at its left and right side. They also, the scientists also identify some basic air movements as, within this basic unit, the street canyon. So the first one, very famous one, is the channel effect. It means that the wind speed is enhanced when the wind is moving perpendicular to the canyon's orientation. So the wind speed is coming in this direction, and coincidentally, the orientation of this long street is parallel to this wind direction. So this wind will accelerate when passing through these long street canyons, and this is called channel effect. And another effect is called Venturi effects, meaning that when the wind has to pass through a small openings, the wind speed will also increase. So this is another methods that we can accelerate the wind. Okay. And another series and observation wind phenomenon we can observe is related to the building height to street width aspect ratio. So the scientists find that this aspect ratio is actually related to the flow patterns. So if our aspect ratio within this range, the flow may easily come in these deep street canyons. So making the flow patterns is isolated. So these flow patterns and this flow pattern is isolated. So they call them isolated roughness flow. But if we increase our aspect ratio, meaning to make our street narrower, what will happen is that these two flow patterns will interference with each other. And finally, some of them will go skipping across through the rooftop level of all the buildings. And this flow, the prevailing wind, cannot enter into the deep street canyons, making that the exchange of the air between the outside free atmosphere and the indoor air, the connection is lost, meaning that the flow, the air pollutants and the anthropogenic heat will accumulate here, and they cannot escape from these deep street canyons. So this is another findings from the science. Okay, so we have already shared with you some basic airflow movement that's surrounding the isolated buildings and the street canyons. So let's go back to our urban area. So our urban area is very complicated because it consists of many isolated buildings and many street canyons. So, but the scientists can still find some general and basic wind behaviors in the urban areas. So the first of all, they find that the urban area will reduce the wind speed. So this is the study we conduct in the past several years in Hong Kong. So we purchased equipment called Doppler LiDAR, and this equipment can help us to have the measurements of the vertical wind speed profile in the field, so that we can exactly know what is the number of the magnitude of the wind speed at different high level over the measurement position. So in this example, we put the, I think I skipped one. In this example, we put the LiDAR equipments, one in the city center at Hong Kong U, and another at the upwind area at Hop Jui. So this one will be, the terrain here is covered normally by the vegetation, so no urban construction is here. And here is one of the high density urban areas in Hong Kong. So this is the equipment, what the equipment looks like. And we can see that this is the observation we have. So this profile representing the one we measure at the city center, so Hong Kong U. And this green line representing the vertical wind speed profile we measure at the Hop Jui, the upwind. So you can see that actually the wind speed reduction is over 4 meters per second. This is a huge number of wind speed loss, meaning that actually we have enough wind resources in Hong Kong, but when we approaching our city center, most of them will be, the wind speed is reduced, so we cannot benefit from this high wind speed, especially during the summer. Okay. And And related to this wind speed reduction, we have a term to explain, to describe these phenomenon. So usually we call them shelter effects or the wall effects. So Hong Kong has many wall buildings, right, because of the insufficient of the land supply. So we will build these buildings in a compact style, so making them will sheltering the wind, and we're sheltering the wind, and then we'll also blockage the coming winds so that the wind will be reduced after passing through these wall buildings. So this is an example I find online, and this is the CFD simulation conducted by previous research, showing that if we add one block of wall buildings, the CFD simulation showing that the wind is actually reduced significantly, the wind speed reduced significantly, so that you can see there are some many more blue areas here at the downwind of these wall buildings. Okay, so even we just have this observation at this simple situation that we connecting 4 different street canyon, you can find that actually the flow patterns will vary significantly just by changing the orientation of the wind speed. So by observing the wind speed coming from the 0-degree direction to 45-degree directions, the wind vector here, they behave very differently, showing that how the patterns behave complicatedly. And similarly, if we did not change the wind direction, but instead we change the orientation of 1 or 2 of the street canyon, we can also find that the flow pattern can change significantly. So now let's go back to our urban areas. So you can observe these CFD simulations results from urban area in Hong Kong. And we can find that actually the flow behave very differently at different part of the city, right? It's hard to predict what they will be at different part. So we use this example to have a more clear explanation. So you can see from these pictures, we have point 1, point A, point B, point C, point D. And at point A, we have the strong flow is deflected down the building. And point B, the flow is quite calm. And point C is like a combination of large buildings restrict from canyons yet accelerating flow. This is what we have already introduced, the channeling effects, right? So you see that we have 3 points, but at these very small urban areas, but they behave very differently, showing that how complicated our urban morphology is. So how can we understand the relationship between the urban morphology and the wind behavior in such a complicated urban systems? Scientists introduce a concept to help us to better describe or quantify this relationship. So they call this concept as boundary layer. So what is boundary layer? And you can better understand this concept by looking at this picture. So the wind, when the wind is coming from the maybe the open sea surface, and the wind is actually laminar, meaning that there's no any turbulence. But when they passing through urban area which have higher roughness, and the flow will be transferred from laminar flow patterns to turbulent flow patterns. And the near ground, near surface flow will change their behaviors. And these regions that the flow has been changed by the ground surface or the urban surface, we call these areas boundary layer. So with the understanding of this concept, boundary layer, we can further have the concepts urban boundary layer. What is urban boundary layer? Urban boundary layer means the boundary layer over an urban surface. So this is how they define the urban boundary layer. And why this concept is important is because that with these concepts, we can further define our vertical wind speed profile at different parts of the urban boundary layer. So, for example, the terrain roughness actually have significant impacts on the vertical wind speed profile. So over the smooth surface, such as the airport, you can see that the wind profile is actually relatively flatter with higher wind speed at the bottom. And then, if we compare it with the high density urban areas, you can find that actually the wind at the bottom is much smaller, right, compared to this one. And the curve of this vertical wind profile is steeper. So meaning that and then you can see that the height of this urban boundary layer is higher than this one. So by understanding this, we can identify to what extent our urban surface, our roughness on the urban surface impact the vertical wind speed profile. And in addition to the impacts of the urban roughness or our urban morphologies, and other key important factors affecting the vertical wind speed profile shapes is the atmospheric stability. So if our atmospheric condition is neutral, the profile will look like in this way. But if our atmosphere is unstable, they will have more vertical exchange in these vertical directions, so making this profile steeper. But if we have less vertical movement of the air, the flow pattern, the vertical wind speed profile may look more stable. So this is the impacts of the atmospheric stability. Okay, so we have finished section 1. So this section 1's information can help us to better understand the following parts of the study in today, because I will go into a more practical part to introduce the building and urban ventilation design guidelines in Hong Kong. And most of the strategy is actually based on the understanding of the theory I introduced just now in part A, in section 1. Okay, so this is the first guideline I would like to introduce to you. Perhaps some of you or many of you may already know these guidelines, but I still want to have an overview of these guidelines so that we can better link to the section 3 and section D. So this urban design guidelines has provide us many air ventilation related design strategies. So they subdivided this strategy into district level and site level. So I will go through them one by one. So this is the first strategy at the district level. So the strategies require us to divide the size into parcels so that to avoid long and linear site geometries. So you can see that because the lay of the building regulations when they do this building design in the city center at Tsim Sha Tsui, we can easily find these linear and long buildings in these regions. So this building design is actually not good for air ventilation. So the guideline, the strategy suggests us to actually separate this into parcels so that we can have more wind can be introduced in these gaps, building gaps, and into the down wall of this building. Here is a design examples. It's not a real design examples, but it is a conceptual design examples that we can find from the previous research. So they used Mong Kok as an example to do this comparison. So the first one is the existing condition of Mong Kok. So many of the buildings are long and continuous and no sufficient gaps between the buildings. And another one is the development with the sustainable principles. So they following the strategies to divide the site into different parcels, small parcels. So this is the CFD results from them, and we can see that after dividing the size into different parcels, you can see that the wind speed is actually enhanced significantly. You can see more red area, right? And the flow now can pass through these regions, but before the redevelopment, the flow is actually not able to passing through this because the building is long. And we can have further comparisons of the redevelopment and before redevelopment and after redevelopment case, and we can see that the wind speed, they use the normalized wind speed called wind velocity ratio to compare the two cases. And we can see that after the redevelopment, the Model 2 has less frequencies of the measuring point that measured low wind speed. In comparison, the measuring point that we called higher wind speeds is increased, showing that actually these strategies can help us to improve our wind speed at the pedestrian level. Okay, and this side disposition strategy can actually be extended to the seafront area. So this is actually another strategies from this urban design guideline. So they highly recommend to separate this building and to separate the size into small parcels near the sea. This is because wind will come from the open areas at the open sea, right? And so this is actually the major source of strong wind. If we block this area, then the wind is not able to enter this seafront area, and they are not able to penetrate deeper into the city center. So that's why they suggest us to have these strategies to improve the waterfront design. So a very famous example is the design of the Hong Kong SAR government's headquarters. And so their design is, because their building is exactly at the seafront, but to avoid this huge building blocking the prevailing wind from the sea, they dig a hole here, right? A very large hole here, and the wind is able to still passing through this huge building and then to enter into the downwind regions. By using this, the wind can not only benefit the building surrounding area, but also the downwind area of these buildings. So this is a very famous example of the AVA in Hong Kong. Okay. And the next strategies is to build the breezeways and air packs. And actually, we have many separate breezeways, like the roads, like the linear park, and like the low-rise building corridors, and also some other building setbacks and non-building areas. But if we did not connect them together, it will not become a breezeway network. So, and this way, if we do it in this way, it is not efficient for the wind to flow, through our large urban areas. So this guideline actually suggests us to connecting all of these small, major or minor breezeways so that we can connect them into a network of breezeway and air paths. And this is another strategies to tell us that actually the street orientation is related to the airflow behaviors. So if we can better align our main street orientation to the prevailing wind directions, we can have a better chance to attract more wind into our urban building arrays, and so that we can have higher wind speed. And this is a similar examples. So if we put our buildings in this way, so the longer facades of the buildings facing the prevailing wind, so the wind will experience more blockage, right? Because of the higher form jack we introduced in section 1, right? So this one is not good for the wind to going through this area. Instead, if we put our buildings in this way, the longer facades of the building is parallel to the prevailing wind, then the wind can more easily passing through it. Okay, and a good example I find is the redevelopment of the upper Ao Tau Gok estate. So before the redevelopment, their building form is in this way, right? Their prevailing wind is coming from this direction, and their buildings longer facade exactly perpendicular to the wind. So making then actually the wind is not easy to passing through these urban areas, estate, right? But after their redevelopment, they changed the orientation of the building, and to exactly this long building in the orientation that parallel to the prevailing wind. So you can see a very clear major wind corridors. And now their wind environment is very much improved. So this is another good design. So they trying to not just building this major corridor, but introduce some minor corridors so that the wind actually, even coming from this direction, they can still have very good ventilation. Okay. So the next strategy will be the street widening. So, I introduced just now that if our street is too narrow, the wind will skimming at the rooftop level, and they cannot enter into here, right? But if we try to widen the streets, then the flow may be possible. More flow can be entered into these streets, so enhance the exchange of the air inside and outside, so that we can have better air quality and more comfortable wind environment. Okay. So and other strategies is the high profile. So this is the so-called downwash effect. So if we build the building in the same height, then downwash effect is not possible. But if we build the building at different height, they will make the flow behavior more diverse, and the downwash effects will occur at this moment. So this is another diagram showing that we need to build our building in a variable height so that we can diverse the flow behavior and we can have the chance to have better ventilation at the pedestrian level or the middle level. So here is the reason or the aerodynamics explanation behind the flow behaviors. So from the left-hand side figure, and we can see that they build the building in this way. So this is the upwind building, this is the downwind building. The upwind building is lower, and the downwind building is higher. So in this way, the wind can pass through here more easily because there's no blockage here. And when the wind approaching this taller building at the downwind side, they will force the flow go down. And here, they will generate a high pressure region at the windwall side of the building. And because here is a high pressure region and here is a low pressure region, and we will have this pressure difference, and the flow here will be accelerated. So we can see a higher velocity here. So this actually is, we call it downwash effects. So in this way, the flow can be enhanced. And on the opposite, if we build our building at this uniform height, so what will happen is that because the aspect ratio in Hong Kong is very high, so the flow tend to skimming the buildings at the rooftop level, so no prevailing wind can going into the street canal. So the flow here is recircle, and the air pollutant and anthropogenic heat will remain here. So it's not good for our health and our comfort. So this is the comparisons of the two phenomena and to explain the reason behind. So even in Hong Kong, we have extremely high street building height to street width aspect ratio. The downwash effect can actually very clearly be observed through this diagram. So the left-hand side, the building has uniform height, and the right-hand side, the building has a different building height, and you can see that. So here, there's no exchange between the inside and outside wind, but air. But here, the flow can enter into here because of the downwash effect. Okay. So meaning that this strategy is still feasible in Hong Kong, although our aspect ratio is very high. Okay. And another strategies is on the design of the podium. We have many large podium, but if we can consider to change the design of the podium from this bulky podium style to individual podiums, then we can allow more wind to passing through our building complex. And more than that, we can also consider to introduce a terrace podium design so that the flow can perform in this way rather than this way, so that they can more easily penetrate in this deep street canal. Okay, so this set of diagram told us another important strategy is to increase the permeability of our building and of our urban area. So, but they have different strategies, and the main concept is that we need to dig more holes, we need to introduce the void decks, and we need to change the orientation of the buildings so that we have less frontal area facing the prevailing wind, and the wind can have more rooms to enter into our building complex so that they can bring more airflow into our urban and building design. Okay. And so, although the urban design guideline give us so many good strategies for help us to consider to be used to improve our air ventilation, but actually the guideline did not tell us which strategy is better or when we should use which strategy. We do not know this answer. And recently, our team did wind tunnel experiments, and to compare these 4 different strategies recommended by the guidelines. So they are aligning street orientation, decrease building coverage ratio, increase permeability, and varying building height. So we use one of the site at Mongkok as an example, and we do this 4 redevelopment case. So each redevelopment case, we apply one strategy recommended by the guideline. And then the plot ratio is controlled as constant for all the case. And so in this figure is the results of the wind tunnel experiment, from the wind tunnel experiments. If the point, this is the measurement point, if the point so this each of the figure is comparisons of the wind speed performance at the pedestrian level before and after the redevelopment. If this point is in green, meaning that after redevelopment, the wind speed is increased. And if the size of this point is larger, meaning that the increase is larger. But on the opposite, if this point is in red, meaning that the flow of wind speed is decreased after the redevelopment. And we can find that actually scenario 4 is the best, meaning that these strategies, at least at the site we test in Mongkok, have better performance. So varying building height, you should consider in your design in the future. And this is another study. We further compare the strategy to link the breezeway and to widen the breezeway. We compare these 2 strategies independently, and we also combine these 2 strategies together. And we find that because the Hong Kong's city center is very dense, relying solely on linking the breezeway or widening the breezeway may not be sufficient to improve the wind. So you can see that by applying one of these strategies, the improvement is only below 15%. But if we combine these 2 strategies together, the improvement can jump up to over 30 or even 60 if in the future case. So in this diagram, we can visualize the wind enhancement distribution. So this is linking the open space, within the open space, and linking past written. And we can see that actually the point size here is much larger than here, meaning that if we really want to use these strategies, better combine them together if the situation allows. Yeah. Okay. So this urban design guideline actually provide us most of the important qualitative recommendation. And actually, the Hong Kong GPC also have a guidebook on urban microclimate studies. And one of the section is related to wind. And they also provide us many very innovative diagram to showing us some quantitative design strategy for improving air ventilation. And if you are interested, you can definitely have a look. but I will not repeat this strategy in this lecture due to the time limit. Okay, so let's go into our next guideline I will introduce is the Sustainable Building Design Guideline. So what's the difference between this guideline and the Urban Design Guideline is that the Urban Design Guideline is looking at the site and district scale, but this one more on the building scale. And the next difference is that the Urban Design Guideline only provides us some qualitative suggestion, but for the Sustainable Building Design Guideline, they provide us some quantitative suggestions, including the quantitative metrics for us to control our geometry of the buildings and the street. So, so there are actually three key building design elements that related to the wind. So one is the separation, and to increase the separation, to increase the building setback, and to increase the side coverage of greenery. But this one is not related to the wind, so I will not highlight this part in this lecture. And the important thing is that in practice, compliance with the APP 152, this is APP 152, is required for developments to seek gross plot ratio concessions, extra 10% of the GFA under the building ordinance. So this is the motivation for some of the architecture programs or urban design program to have a compliance with this APP 152. So I would like to introduce it a bit here. So the first parameters they introduced to us is the LP and the U. So LP is actually the continuous project facade length, and the U is the width of the street canon. So how can we use these two parameters? They're actually one pair of parameters. So they tell us that we cannot build our building with a too long facade. So the relationship is here. So we should not build our building. The maximum allowance of the length of this building is 5 times of the street next to it. And this example is the same. And there's a different width of the street adjacent to the building. So we can only take the narrowest one as the reference to do these calculations. So meaning that this length of the building, the dimension, this LP of the building is actually 5 times of this one, but not this one, yes. And this one is the same. The LP is, the maximum is 5 times of this one, but not this one, because this one is narrower than this one. So we cannot use this one as a reference to do the calculation. We can only use this one. Okay. And the next one is the S. S means the separating distance. And the S, how they control this S is that between the projective facades of the building and the side boundary of the center line of the adjoining street length should not be less than 7.5 meters. So if this is the street, so this is the center line of the street. So between this center line and the building's facade, project facade, so the minimum distance is 7.5 meters. So if this is the side boundary, between the side boundary and the projective facade of the building is also the minimum requirement is 7.5. So this is how they control this S. And the next one is the permeability. So permeability means that we have vertical sections to do the assessment. So they have 2 types of permeability elements. One is called intervening space. So this one in white color. And another is the permeable elements, so PE, so it's these elements. So the area, the total area of this Y area and this area divided the total area of the vertical section assessment area, they have to fulfill the minimum requirement of 20%. So this is the, and of course they have more details requirements for different situations, but for most of them, they have to more than or not less than 20% of the total permeability. Okay, so we know that these 4 different quantitative control metrics from the Sustainable Building Design Guideline, but actually we have more parameter or metrics that can control our building's performance in terms of better ventilation. So one of this famous indicator is called frontal area density. So this one is actually similar to this permeability, but for the permeability, they calculate the ratio of the openings exposed to the prevailing wind. But this one, they calculate the frontal area of the building exposure to the prevailing wind. So different calculation, but similar meaning. They are all controlling the permeability. And in Japan, in the KASB system, they also have these similar indicators. So this one, they call it percentage of exposure area. And you can see that they are quite similar, right? So they have this vertical assessment section, and then they also have this frontal area of the building, and then they calculate the ratio of the area of this building to the assessment section area. So this one is actually they call it building spacing index. So it's actually quite similar to the aspect ratio, but this one is, when they do the calculation, they have a section that is parallel to the prevailing wind, but this one, they have the section is perpendicular to the prevailing wind. Okay, and we also have a literature review on the other more also important parameter to control the design of the open space. And we, according to our literature reviews results, we summarize 10 most important parameters that are related to the air ventilation performance. And this is the different parameters. We have it's the well load, the planned area ratio, right? The line density of the street center line, and then the sinuosity and orientation angle of the street intersections, and the length and the width of the street, and also the permeability and the average building height, high variation, and the aspect ratio. So actually most of them we have already been covered in my talk in the previous parts. And then here is what I want to highlight to you is that actually not all of this indicator attracts enough attention, and the most frequently used parameter is this coverage ratio, the building aspect ratio, the building coverage ratio, or the permeability. And then we can also see that actually the high variations and the aspect ratio and also the wind to street angle has more attention, so more widely used. So you can find that actually this 5 indicator may be more frequently used and can attract more attention of you. Okay, so this is the section 2. Okay, so we can going into section 3, the methods to assess urban wind enhancement. So after the introduction of some background information of the aerodynamic knowledge and the practical aspects related to our building and urban guidelines, so we finally going into the method part. So for the method part, actually we have 3 main methods that are commonly used to study the urban wind environments. So this is the classification according to this very famous book called Urban Climates. And if you are interested, you can borrow from a library to read. And so in this book, they summarize 3 different methods in studying the urban climates. So one is the field observation. So we use the equipment to do the measurements of our urban environment, urban climate. And the other two methods is physical modeling and numerical modeling. So physical modeling meaning that we need to have a lab to do some experiments of the wind. So this has to require some physical, reduced scale physical model to be put in so that we can finish the experiments. And the next one will be the numerical modeling. So we rely on the numerical software, the CFD, to do the simulations. So the difference of these two is that this one rely on the physical model, but this one we don't need any physical models. We just rely on our computer. We need a license, right, to run the software. Okay. So there are actually three very basic wind performance variables we need to know. So of course, the wind speed, right? Wind speed describes how fast the air is moving past a certain point. And the next one will be the wind direction, because wind has direction. It can come from north, come from south, come from west. So the wind direction is very important because it's related to our street orientation and building orientation. So it's related to our design decision. And the next one will be the turbulence intensity. So actually the turbulence intensity is calculated from the wind speed, but it describes the fluctuations of the wind speed related to the mean wind speed. So how frequent the wind speed is changed, this is the turbulence intensity. So this is also important because when we do CFD, we need to input the wind speed as the boundary condition, and we also need to input the turbulence intensity as the boundary condition. And we also need to define where this wind is coming from. That is the wind direction. So we have to know these three wind performance variables. Otherwise, we cannot finish our boundary setting for the CFD and AVA. Okay. So there are actually three types of the field measurement type. So the first one, we call it the fixed measurement type. So we have the equipment that fixed on a particular point. So to do the measurements at this fixed point, so this is called fixed measurement. And if we put this measurement equipment on a vehicle and it is motable, then we call this measurement type as mobile measurement type, right? And sometimes we also not just need to measure the wind near the ground. We also want to measure the wind at the vertical direction, right? So what we can do is traditionally we can put our sensor and anemometer or in the balloon, and then the balloon will rise, right? And then when the balloon rise to different vertical level, they can do the measurement at different levels. So this is the flow following. It is also one of the mobile measurements, but this is in vertical direction. Okay. So this is the basic way we can do the measurement. So this is most of the available types of anemometer for us to do the measurement of the wind. So some of them are three-dimensional, some of them are omnidimensional, and we have the more traditional anemometer like the hot wire anemometer and the cup anemometer. And we also have the more advanced anemometer is ultrasonic anemometer and laser anemometer. So the difference is that this one is less accurate. This one is more accurate, but this one is more expensive. This is less expensive. So anyway, we have a wide range of selections up to your needs and up to your budget. Okay. And if you we don't have money to purchase the anemometer, right? Because they are expensive, and if we don't have a project to support it, it's quite difficult for us to buy an anemometer by ourselves. But we can actually obtain this data from Hong Kong observatories. They actually have these free data sets from their website. So this is the location of all the automatic weather station and the other weather station distribute across the whole territory of Hong Kong. And some of them provide the wind speed and wind direction data on an hourly basis and daily basis. So this is the one of the example that I find from their website. and they have many different type of equipment, and we can find this equipment are measuring different variable of the climates, and some of them are handling the wind speed. This one is the anemometer. So they have the anemometer that they can obtain the wind direction and wind speed. Okay. And the next main method is the modeling. So why we need to have the modeling instead of the observation? This is because if we do the observations, we can only know the measurement value from one particular point on the Earth, right? So which is maybe not enough for us to do the air ventilation assessment, because we may need more test measurement points. But each measurement point, if we do field observation, it is very expensive. So perhaps for some of us it's not affordable, but modeling can help us to improve this, to solve this issue, because in the CFD simulation or wind tunnel, we can put many test points surrounding our test area, so that we can have a whole domain's data of the wind speed. So, and then the cost is much less than the money that we need to purchase the equipment. But before I go into the introduction of the modeling, and I would like to highlight two main differences between the modeling and the observation. So first of all, when we do modeling, the first thing we need to do is simplification. We need to simplify our models. So this is because the computational resources is limited. The computer power is not able to simulate all of the details in the real world, in the reality. So we have to simplify our models. So this is the three examples I find from the previous publications. And so this one, you can see that actually when they modeling this urban area, they simplify the geometry in this way. So actually all the facade detail is gone, and the greenery is gone. And so this is the way how they simplify their model, so that they can put into their computer software, and then the software will not crash. And this is another example. When they do this simplification, you can see that actually the building become very regular shape, and then most of these details on the facades and surrounding the building is gone. So this is another example of simplification. And another simplification is the study when they're doing the investigation on the cooling effects of the trees and greeneries. And what they do is to build these very simple geometries to represent all different species of greenery. So this is, but in reality, this greenery is not look in this way. So this is the way they do the simplification. Yeah. Okay. And so it means that actually the modeling cannot help us to capture all the features from the reality. So this is the disadvantage of the modeling. We will lose some information from the real world. But the advantage of the modeling is that they can provide us a better way to control our experiments. So this is the example I find from previous studies. So if we want to test the flow that coming in a twin stick way, or coming in a 13 degrees Celsius, 13 degree angle or 15 angle, in the reality, when we do the measurement, it's difficult for us to control, right? Because we cannot control how, from which direction the wind is come from, right? We have to wait. But in a lab environment, we can do this more precise control of the angle of the coming wind speed, right? So similarly, if we want to test different patterns of the building designs, so this is the 6 different patterns consisting of four same buildings, but in different layout. So they can easily do it in a CFD simulation. But in real world, it's difficult for us to do this comparison because we may not have enough budget to build these buildings in the real world only for an experiment, right? So, but in CFD, we can do this simulation very easily and budget friendly. Okay. But when we do physical modeling, I mean wind tunnel modeling in the lab, what we need to do is to reduce our model. So if we are testing one single building, we may need to reduce this building model to 120 scale. And if we want to put a larger models like an urban model in the lab, we need to further reduce our models to 400. So in this way, we can allow the lab to contain our urban or building model. But please bear in mind when we do this physical modeling, we need to keep the geometry similar as they are in the reality, as they are patterns in the reality. So it means that a physical model need to require the length, dimension, and the angle of the prototype to be scaled consistently in the model. Okay. So this is the lab we used 2 years ago to do a wind tunnel test in Hong Kong University of Science and Technologies. So in this wind tunnel lab, this is the test chamber and a very simple chamber. But you can see that actually it has 6 phases. So 2 lateral wall, 1 ceiling, 1 floor, and 1 outlet, and 1 inlet. So the inlet will let the wind coming through it, and the outlet will let the wind escape from this test chamber. So what we did is that because the very first step when we do the wind tunnel test is that we need to reproduce the real-world vertical wind speed profile. So if we have nothing on the floor, the wind will perform in this way. So the wind speed will be similar at the bottom to the ceiling. So in real world, it's the same. If the wind is go over a smooth surface like the open sea surface, then the wind speed will be constant at different vertical level. But when it going through a roughness surface, the flow at the vertical wind speed will have the curve, and if the roughness is higher, then this curve will have a sticker form. And so to reproduce these flow patterns, this vertical wind speed profile, we need to set up this wooden block in the upwind area of this test chamber, so that they can simulate the roughness, this vertical wind speed profile observed in the real world. And by putting this roughness at the upwind area, we can change this flow from this inlet from this curve to this curve. Okay. So this is the very first step, and this is our team and the staff in this lab. So we work together to setting up this roughness at upwind. And after setting the upwind, we have already calibrated the vertical wind speed profile. And the next step is to set up the urban model because we not need to test the wind performance at the production level in this urban area. So we need to put our urban model at the test area. There's a turntable here. So this will allow us to have a turning of the urban model, putting on top of this turntable, so that we don't need to manually rotate these models. So why we need to rotate this model is because that they can allow us to test different wind direction, because the AVA and CFD require us to test the wind direction, 16 wind direction from different, from east, from west, and from north. And after putting the building models on top of this turntable, we also need to put the sensors at different places of the street. And then this sensor has to connect by cable and then go back, the signal will be transferred to the receiver, and then they will help us to collect the data. So this is a video I find, and actually it can show us how. Actually this video can let you to have a look at how a wind tunnel experiment looks like. So you can see that the wind is actually coming from the inlet. This is the inlet, and this is the roughness elements. So when the wind passing through this area, the vertical profile will change, and then it will approach this urban area, and then this is the turntable, and because it can turn in different directions, so that it can test 16 different directions, so that to have a comprehensive assessment of the pedestrian level wind speed. Okay, so this is an example I find to tell you the physical modeling part. Okay, so let's resume the lecture. We just talk about the numerical modeling. So actually, the numerical modeling need to solve these different sets of equation, including the mass equation, momentum equation, and energy equation. We'll not go through this part in details, but we're going into the other important parts of the numerical modeling. First of all, we need to understand that numerical modeling actually has different scales. So from the larger scales to smaller scales, it will require us to input different details of the geometries. And of course, for our AVA and CFD, we will need to input the building geometries in a more detailed way. So actually, the CFD is actually, we need to handle the neighborhood and building levels details. So this is the scale we are falling in. And the second part is the software. So actually, there are different types of software available in the market. So we can classify them into two categories. One is open source, one is commercial. Open source means that it's free, and commercial means that you need to pay, right? And the advantage of the commercial software is that it will with a graphic user interface. So you may, and some of them will have the technical support, meaning that it's more user-friendly. But for the open source software, because it is free, so most of them has no graphic user interface, and you may need to know some skills of programming. So, and this is the typical CFD flow, workflow. So actually they have three different stages. So pre-processing, processing, and post-processing. Meaning that at the pre-processing, you need to prepare your geometries, you need to set your CFD domain, you need to define your boundary condition, and to setting your analyzed controls. And analyzed control means that you need to set your turbulence models and also the convergence criteria. And after that, you need to perform the gridding and meshing. And processing means that you need to run your prepared models. And after the processing, you need to output your data in the way that you would like them to be output. So this is called post-processing. Okay, so there are three main guidelines I will recommend to you. So this is all the famous guidelines, user guidelines to help you to understand which type of settings you need to use which parameters values. So this one, cost guideline is from Europe, AIJ guideline is from Japan, and this 10 tips from Professor Brocken is a guideline that recommended by this professor in Europe. Okay, so we have talked about the computational domain. So this is the first step when we do the CFD setting. And why we need a computational domain? It's because, so for example, we are going to test the wind speed of this target site. So why we need a domain is because the real world has no domain, but we cannot put the whole real world into our CFD model, right? Because it's not affordable for the computer. So we have to tell them where is the boundary we are going to do the simulation. And okay, so this is the computational domain. So you may ask another question, why we need, okay, I already answered you why we need a domain. So the next question is why we need a bigger domain. So why we have to do this, but we cannot do this smaller domain because our size is just very small. Why we cannot do this smaller domain? That's because actually in the real world, this domain is not existing, right? So if we put this domain, it will actually affect the wind. So when we do the simulation here, this domain will affect the flow flowing through this. So if this domain is too small, actually it will impact the flow that near here, and then it will give us additional and unnecessary wind pressure to the flow surrounding this area, so making the results of around our target area not accurate. So that's why we need to have a larger domain in this way. So how big a domain size we should use? Okay, then we can refer to the 3 guidelines I suggest for you just now. So according to one of the guidelines, the cost guideline, we will require 5H at the lateral side and the upwind side, and also the between the ceiling of the tallest building to the ceiling of the domain, the computational domain. And then for the downwind side, they suggest to have 15H. So this H is the maximum height of the building within your target site. And because we have a different requirement from this cost guideline, different requirement of the distance for the upwind and downwind. So actually it is sensitive to the wind direction. So if the wind is coming from this way, then we set 5H at this upwind area and 15H at this downwind area. And if the wind is coming from an opposite way, we have to switch the distance settings. So 5 will be from here to here, and then 15 will be from here to here. And of course, there's another setting requirement, like for the AIJ guideline, they will recommend like 10H from different directions. So it's up to you to choose, and you can do a sensitivity test to ensure that this distance is sufficiently long, so that this non-existing wall in the real world will not affect too much of the airflow near your target area. And okay, this diagram is to actually further explain why we need a longer distance between your building to the downwind boundary. This is because this wake area, this flow recovering area, downwind area, is very long. So to ensure that this flow can freely develop, so we need a longer distance between the downwind boundary to our side. Okay. And after we set the domain, we also need to set the boundary, same as the setting we have observed in the wind tunnel lab. We need an inlet, we need an outlet. We also need 2 lateral walls, and we also need a ceiling and a surface. So we have 6 facades normally for simulation for urban case. So this is the 2 examples. So we have 6 walls, right? So this is the inlet, this is the outlet, and this is the lateral wall, and this is the ceiling, and this is the floor. And for the different boundary, we need to set a different computational boundary condition. So this is the inlet, we will need to input the inflow, and this one we need to set the outflow. And then for the top and the lateral boundary, we need to set the wall function. And for the ground surface, because we need to let the flow to experience some roughness before entering our urban area. So we need to set the rough wall function. And after we set the domain and the boundary condition, what the next step is we need to do the numerical discretization. So because we need to tell the computer in what resolution, spatial resolution, we need it to generate the simulation results. So we need to subdivide our domain into different pieces, and each of these small space it's a computational cell, and within this cell we will have one number of different variables we are asking the computer software to calculate. So one cell will contain one wind speed. Okay. And this is how the mesh look like. We actually has two different types of mesh. One is unstructured mesh and another is structured mesh. Structured mesh is more regular and it is Cartesian system, and unstructured mesh can better capture the details of the building geometries, especially those on the facades or the very small elements in our urban area. And after setting the meshing, the next step is to configuring the analyze control. And there's a different turbulence model we can select from RAMS and LES and DNS. And RAMS is actually to solve only the time average flow with turbulence model. In our AVA tests, they actually require us to use the RAMS. And for the LES and DNS, they take longer time to do the simulation. And of course, they will provide more accurate simulation results because they will solve all or partly the turbulence eddies. But of course, the cause is that you will need longer time. So it is not required by the AVA at this stage. Okay. And this is the example I find online to showing you that an LES simulation. This is the area, one of the urban area in Macau. So this is just a simulation that you can see the flow patterns passing through this urban area. Okay. So to have a summary of this part, so we introduced the observation, we introduced the modeling methods. So what are their advantages and disadvantages? So for the field observation, the advantage is that it actually records the real-world condition. But the disadvantage is that it lacks of experimental control. And in comparison, the physical modeling actually it is also expensive, and particularly it needs some specified facilities and manpowers, right, in technicians to support this modeling. And of course, because it is conducted in a lab environment, so your model need to be the scale need to be reduced. So you need to ensure the similarity of their geometries, so that before you do the experiment, so that your result is reliable. Still consider. And for the numerical modeling, an advantage is that it is budget friendly. But the disadvantage is that compared to physical modeling and field observations, there's no any measurement data. So you need to do a validation of your numerical model before using it to do your parametric study, so that you can convince the others that your simulation is accurate and reliable. Okay, so this is the end of section 3. So we are going into the final section, air ventilation assessment method. So the motivation for Hong Kong to establish this air ventilation assessment system is because, of course, for introducing more wind and better ventilation in our very dense urban environment. And this is very important for Hong Kong because Hong Kong is famous for its high density and complex urban morphologies. And it is crucial to improve our understanding of the pedestrian level wind environment and vertical urban wind speed profile to support the urban climate modeling and urban design. So in 2006, the AVA system was introduced in Hong Kong, and to provide systematic methods to assess the impacts of urban design on pedestrian level wind environment. And what I want to highlight here is that together with this AVA system, the government also established a set of vertical wind speed profile data. And this vertical wind speed profile data, they call it side wind availability data. So this data is very important because they are supporting the AVA and to providing the necessary boundary conditions. So the boundary conditions play an important part because the more accurate of this vertical wind speed profile as the input and the more accurate the output from this AVA. I will introduce a bit more details later. And for the project, actually AVA did not require all projects to conduct the tests. So they separate they have different requirements for the government project and non-government project. For the government project, all major government project normally is required to participate in this AVA test. But for non-government project, it's voluntary basis. But they have non-government project will have motivation to participate in this AVA test because if you can pass the AVA, maybe it have the potential to help your project to add some property value. Or, for example, in the Hong Kong GPC's assessment tool, they will give you extra credit points and bonus. So this is all the extra motivation for non-government project to join this AVA test. Okay. And for the AVA test, it did not rely on the absolute value of wind speed as the evaluation indicator. Instead, they use a normalized wind speed as the indicator. They call this wind velocity ratio. So how to calculate this wind velocity ratio? So this is the equation. So the wind velocity ratio, they use the symbol VR. Actually, it is the ratio of the wind speed at 2 meter height at the pedestrian level and to the wind speed at upper level, so slide 500 meter high. So why they use the normalized wind speed instead of using the absolute wind speed at the pedestrian level? That's because the side wind availability data, when they establish this AVA system, they are relying on numerical modeling and physical modeling. So actually, no reliable measurement of the wind speed at upper level across the whole territory of Hong Kong. So because of this late measurement data of the V infinity, so they decided to use the normalized wind speed rather than the absolute wind speed. So the purpose of the AVA is actually to help us to compare the relative difference of different scenarios we are testing in the AVA, rather than find out the absolute performance of the wind speed of each of the scenario. So this is the key difference between the absolute wind speed and the wind velocity ratio. So for the AVA, actually there are 3 steps. One is expert evaluation. The other 2 is initial study and detailed study. For the expert evaluations, there's no any requirement for running simulation. So you can consider it as a qualitative assessment. So they just require you to identify the good design features and the problems areas that need mitigation measures. And of course, they need to determine whether this project, this study, should be staged into the initial study and detailed study, which requiring simulations. But of course, although I said the expert evaluation is kind of the qualitative assessment, but in some expert evaluation, actually they also involve some assessment that using some simple geometry indicator to help them to finish the assessment. So this part will be a little bit quantitative, but overall it requires no quantitative assessment, only requiring a qualitative assessment. And if this project has been determined to need to do further investigation, they will go into the initial study and detailed study where you will need to use the wind tunnel and CFD simulations. So for AVA project, in general, they need us to test 16 wind direction. But for the initial study, they allow some simplification. So we only need to simulate the probability of the wind coming from the reduced set of direction that are exceeding 75%. So no need to finish all 16 wind directions. So finishing 16 direction is a huge work because one scenario you need to do the simulation for 16 times. And if you have more than one scenario, then you need to run many simulations. So so for the initial stage, they allow this kind of simplification. But for the detailed study, no simplification is allowed according to the technical circulation we can find online. So, and the wind AVA process is similar to the CFD and wind tunnel process. They also have the pre-processing, processing, and post-processing. For the pre-processing, you need to prepare the building urban model. You need to prepare the inlet vertical wind speed profile from the side wind availability data. And at the current stage, the AVA do not require us to input any heat flux or the radiations related microclimate conditions. It only requires us to do the CFD in a neutral condition. So this part is not required. So we only need to run the CFD or wind tunnel in a neutral condition. Okay. So here is an example. I find that using wind tunnel, this is the example of the redevelopment of Kai Tak. And another example is the redevelopment of the Hazen Place, and it introduced some permeability at the middle level of the building. So they use CFD to finish this AVA test. So this is two examples using different methods. Okay, and for the AVA assessment, they classify the area of the ground surface into three different types. So the first type is the project area. This project area includes the project side boundary and all open area within the project that pedestrians are likely to access. And for the assessment area, so this one in red is the assessment area. So the radius of the assessment area is actually 1h, and the h is the maximum height of your building of your project. And for the surrounding area, this area in gray is the surrounding area, and the radius of this surrounding area is 2h. So h again is the maximum height of the building of the site. So why we need to include, so your building is here, so why we need to include the assessment area and the surrounding area? That's because AVA require us to simulate the impact of the surrounding. So the wind, if we remove this surrounding area, the wind will approach this target building directly, then it's not realistic because the wind in the real world, they need to pass through this surrounding before entering approaching your area, your building, right? So to help us to simulate this surroundings impacts, they require us to have this surrounding area with a radius of 2h. So this is the setting and the reason behind. And for the test point, they also classify the test point into three different types. So the first one is this test point that is putting in the project area. So this in the very mid center one is the test point in the project area, and the overall test point will be putting at both the project area and the assessment area. And of course, there's some other special needs for testing point, but this two is the more common test points. And the detailed AVA test will require us to report both the this test point and this test point. Okay. So now let's talk about some side wind availability data. So the side wind availability data is actually the vertical wind profile data in Hong Kong. So currently, the government has established two different sets of vertical wind speed profile data. One is simulated by RAMS model. So this is the simulation-based data. And another is wind tunnel-based data. So what's the difference? And you can find this data from the Hong Kong Planning Department's website. So this is the link. You can click into it, and you can find a list of data. And the very top one is the numerical, the numerical data simulated by the RAMS model. And the rest of them are the data set that obtained by wind tunnel experiments. So what are they? So this is how the RAMS data look like. So you can see that this is the whole territory of Hong Kong. And they divide it into different cells. Each cell is 500 meter times 500 meter. And if you click into one of them, and you can find this data. So this data is actually providing you the vertical wind profile in different direction sectors, or they can also provide you the detailed wind speed data or wind direction data at 500 meter or 300 meter or 200 meter. And another data set is from the larger scale wind tunnel. So in the past, Hong Kong still has this very large wind tunnel lab, and they do a wind tunnel simulation at this following test point. And for each test point, they input this 2,000 topography models, and then they can help us to simulate the upwind topography impacts before they entering this test target area. And then they can obtain this vertical wind speed profile and the vertical wind turbulence intensity profile. But the advantage of this data set compared to the RAMS data set is that it may be more accurate because it is complete by physical modeling by wind tunnel. But the disadvantage is that because this test is quite expensive, and they only have this limit size of the wind data. But for the RAMS data set, they actually cover the whole territory of Hong Kong. So these two methods, you can choose either of them when you want to use it as the input for your CFD or AVA test. And alternatively, the Hong Kong GBC Beam Pass also recommend an alternative method to reproduce the vertical wind speed profile. They recommend this power law and log law. So this is also very common suggested by the CFD guideline. So this is what every variable means. And so you can see that to complete the calculation of these two equations, you firstly need to know the terrain-related variable. So for the power law, you need to know the power law exponent, which is alpha. And this alpha is related to the type of the terrain that the upwind side you are going to test in your AVA, in your CFD. And for the log law, you need to know about the roughness length. So this is also related to different terrain type. And another input you would need to use to finish this calculation is that you also need to input a wind speed at the height from the ground. Sorry, this one, the wind speed at reference height. So this one is an necessary input. If you don't have this data, you cannot finish the calculation of this power law and wind law. So how can we find this wind speed at reference height? So one option is that we can refer to the RAMS data sets. So because they not just provide the vertical wind profile, they also provide the detailed wind speed data for annually, summer and winter, and then you can find the 500 meters one and then use this wind speed at 500 meters and wind turbulence intensity in 500 meters and to finish the calculation of that power law or log law calculation. And alternatively, we can also find the data from Hong Kong Observatory. So they have wind speed, wind direction information at some of these automatic weather stations. And then you just need to find the nearest weather station that next to your project site, and then you use their data, and they also provide the location and the altitude of this anemometer at the site, at the weather station, so that you can obtain this reference height and reference wind speed from the weather station. So these two options are both okay to support you to finish the calculation of the power law and log law equation. But at the time that they are establishing the AVA, actually they do not have any reliable measurement devices that can measure the vertical wind speed profile. So what we are doing in the recent years is that we are using this LiDAR equipment to comparing different vertical wind speed profile. We put it into the CFD, and then we do the calculations, and then we comparing the performance of different side wind availability data using our LiDAR observation as the benchmark, and to do this evaluation. And we find that actually this is the wind tunnel side wind availability data, RAMS availability data, and the power law, and this is another vertical numeric measure scale modeling data set. So by comparing these different side wind availability data, we find that actually, so at this suburban area, most of them perform very well, especially for the power law measures and the RAMS measure and the wind tunnel measures. But for the city center, okay, they are perform worse. But they still have, some of them are still perform better than some others. So for example, for the wind tunnel and for the power law, so they all perform better than the others. So here is the takeaways. So our finding finds that if we comparing the wind tunnel side wind data and the RAMS data, we find that the wind tunnel data can perform the best. However, the wind tunnel data is not available at all the sites. So power law can be most optimal options that achieve the best balance between the accuracy and the data availability. So how to use the power law? You can refer to the Hong Kong Observatories, refer to the Hong Kong GBC's the guideline. And okay, the final part is that we also want to introduce the relevant credit points in the BEAM Pass. So actually the BEAM Pass provide us many different assessment tools. So actually because all the guidelines and methods I introduced is actually related to us to build a sustainable city and building. So they all include different parts of these guidelines I introduced just now. So for example, for the new building assessment tool, there is a section called sustainable sites, this SS. So we can easily find these credit points related to the guidelines I mentioned just now. For example, this SSA is related to the urban design guideline. This part is related to the sustainable building design guideline. And this is the SSA part is related to the air ventilation assessment guideline. And this is the more detailed description to helping you to answer you how to more accurately use the CFD to do the AVA test. So you can find this information from the Hong Kong GBC's website. So finally, I would like to introduce our recent study. So because CFD and wind tunnels still need you to have some specific skills and facilities, but we are doing some new attempts to have some more simple methods to help you to have an alternative assessment method of the wind speed. So this is the example we are doing, so relying on the least cost path methods to do some automatic calculation so that we can have some very quick simulation without requiring any specific skill from the users. So we are still developing these methods, and hopefully we can develop this method to help you to save your time when doing the air ventilation assessment. So this is the end for our lecture. Thank you. So for the first questions in the wind tunnel, how to measure the wind velocity? I cannot see the sensor in the photo. And okay, we can go back to the wind tunnel part. So for this wind tunnel, actually our purpose is to measure the wind speed at the pedestrian level. So we put our sensor at the pedestrian level. So for this one, you can see from these images. So here actually is the wind speed sensor. So every point referring to one sensor. So this is, I hope that this figure can answer this question. So for the next question, for CFD simulation, if the upwind distance is set larger than 5h, say a double as 10, how will that influence the simulation results? Okay, so this is a more complicated question. Let me see. So here, so why the guideline did not suggest to make this 5h longer? This is because for this upwind area, the purpose is to maintain the inflow from the inlet boundary to the incident position. So, and the roughness here is actually not sufficient to support the purpose of maintaining the profile from the inlet to the approaching position. So in this way, if this distance is too long, the wind profile passing through this area will be accelerated too much. If this happens, when the vertical wind speed arriving this position, the shape of the wind speed is not like the one that from the inlet. So that's why the guideline did not suggest this distance cannot be too big, be too large. But however, to find a more proper distance, we rely on the sensitivity test to see what is the optimal distance we need for your special case. Oh, how to consider whether the project needs to process to initial study or detailed study? Oh, I believe that this question you need to ask the Hong Kong Planning Department, because I actually don't know how they do this evaluation. Yeah.
So we thank you, Professor He, his wonderful presentation. We would like to also extend our special thanks to the Environment and Conservation Fund for their continuous support. Thank you all of you for joining us today. The attendance certificates for this course will be sent to the participant by email within around 1 to 2 weeks after all questionnaire has been certified. Please stay tuned. Furthermore, as part of the Environment and Conservation Fund Green Building Education and Capacity Building Program, we will be launching a series of upcoming courses. If you are interested, please continue to follow our official website and social media channel for the latest update. If you have no further questions, you are welcome to leave now. Thank you.